Hello, how are you? I hope you all are well. It is very important in this critical time to stay safe, stay at home, stay safe, and take care of your family members too, particularly the elders. You look after them, and I hope you all be ultimately safe, and we together will win the battle against corona. Now let's come to the actual curriculum, right? I won't consider, say, bigger parts at a time, rather small portions in a particular session. I'll come to you later also, and one by one we'll discuss this, right? Today our topic is Fajan's rule. Fajan's rule. The term perhaps you already have heard during your 11 and 12 courses. I'm not sure, but you may. It tells about the partial covalent character that develops in an ionic bond. As you know, in an heteroatomic covalent bond, some kind of ionic character polarization actually takes place due to the difference in electronegativities. Here in case of ionic bonds also, these ionic bonds are not truly 100% ionic actually. Some kind of covalent character actually is developed, is there in our ionic bonds, so-called ionic bonds. And that is governed by Fajan's rule. Actually, when an anion, say this is an anion, approaches to a cation, I deliberately am doing this because cations are generally speaking smaller than anions. So in anion, the electronic charge cloud is rather more dispersed over the space, and in cation there is a net positive charge. As the anion approaches the cation, this electronic charge cloud, the negatively charged cloud, actually is not remains in this manner. Rather it gets polarized. And as it comes nearer to the cation, naturally the polarization increases, and ultimately when it actually falls over the cation, then this part intrude into the cation. So this is the part where you can consider this kind of overlapping. That's how a kind of covalent character also develops in an ionic bond, making the union not 100% ionic, so to say. So it depends upon the polarizing, which actually gets polarized. The anions gets polarized, right? And who polarizes the anion? The cation polarizes the anion, right? So it depends upon the polarizing power of the cation as well as the ability of the anion to get polarized. That means it's called polarizability of the anion. Now, the polarizing power of the cation depends upon, naturally, the charge density. Ultimately, the positive charge density over the cation. In turn, it is dependent upon, naturally, it is dependent upon the size of the cation, the smaller the size, the charge density will be higher, will be greater. The overall charge of the cation, that means the charge, the more the charge, the more is the charge density. Naturally, the polarizing power of the cation is more if the charge is more and the size is smaller. Similarly, the polarizability of anion is again depends upon the size of the anion. Actually, since the electron cloud will get polarized, so the larger the size of the anion, easier will it be for the charge density to get polarized naturally, isn't it? The larger the size, that means the electron charge cloud goes farther from its nucleus, positive charge. That means it becomes more easy to get polarized. Similarly, the more the charge of the anion over the anion, naturally here the polarizability of the anion will be greater. And there are some other factors too, as for example, say a cation is formed when the outermost shell is removed from the atom, from a neutral atom. Now, resulting a kind of inertial ionic cationic configuration could be NS2 or NS2P6, right? Understand? Or could be NS2P6 is some sort of inert gas configuration. Barring helium, all other inert gas do possess this NS2P6 configuration. So cations can have those NS2P6 configuration. Otherwise, from fourth period onward, these cations may also have kind of NS2P6 N-1 D10 configuration. That means a cation can have 8 electron cation at the outermost shell, or could be 18 electron. The power of polarization, that means polarization power of an 18 electron cation is more than an 8 electron cation. That means, now if you compare the polarizing power of lithium ion, sodium ion and say potassium ion, then theoretically all will have +1 charge, but size of lithium ion is smaller than that of sodium, which is again smaller than that of potassium. So the polarizing power of lithium ion is greater than that of sodium, which is again in turn greater than that of potassium. It's understood, right? Similarly, say of the same period, if you go by higher charge, say compare sodium, magnesium, aluminium. All belong to the same group, same period of the periodic table, but the charge of sodium ion is +1, that of magnesium ion is +2, and that of aluminium ion is +3. So the polarizing power of sodium is less than that of magnesium, and that of magnesium is lesser than that of aluminium. So if you consider, say, sodium chloride, NaCl, magnesium chloride, MgCl2, or aluminium chloride, AlCl3, then you will find the ionic character in sodium chloride is more than that of magnesium chloride, which is again more than aluminum chloride, because the chloride ions in sodium chloride is less polarized, more polarized as the charge density of sodium ion is less than that of magnesium, so the polarizing power of sodium ion is less than that of magnesium. Naturally, the covalent character in magnesium chloride is more than sodium chloride. Similarly, the covalent character in aluminum chloride is even more than magnesium chloride, because here the charge of aluminum is +3, right? So the polarizing power of aluminum is much greater than that of sodium. So in fact, if someone asks you that what could be the probable trend of melting point of sodium chloride, magnesium chloride and aluminum chloride, well, in that case you may say, is it possible for me to remember all the melting points? No, it's not required. You can compare. Nobody asks you what is the melting point of sodium chloride, or so to say, what is the melting point of aluminum chloride. Rather, which one has a greater melting point. Then you may judge which one has a greater ionic character. The more the ionic character, the chances more is its melting point, because then in that case the association, the intermolecular, interparticular force of attraction is more in case of ionic compounds. All of you know, right? So in that way you can compare the so-called melting points or different kinds of physical properties also with this percent covalent character, that means Fajan's rule. Now, if two cations have almost same size and charge, then which one has a greater polarizing power? In that case, you check the electronic configuration of the cation. As I said, Ns2p6 or Ns2p6 n-1d10. That means simply we can consider, say, 8 electron cation or 18 electron cation. As I said, 18 electron cations have a greater polarizing power than, say, 8 electron cations. That means say calcium ion and mercury ion, mercury 2+, Ag2+ and Ca2+. Both has almost comparable size and both have +2 charge. Still, the covalent character, partial covalent character in mercury chloride is much greater than that of calcium chloride, as the polarizing power of mercury 2+ ion is more than that of calcium 2+. So chloride ions in mercury chloride is more polarized, hence actually providing a greater covalent character in mercury chloride. Now, let me ask you a kind of a bizarre question. Stannous chloride, that is SnCl2, and stannic chloride, SnCl4, both are actually the chlorides of tin. Stannous is of lower oxidation state chloride, +2, and stannic is in +4. Where stannous chloride is a high melting solid, stannic chloride is a viscous liquid. Interesting. What does it mean? That means the intermolecular force, interparticular force in stannic chloride is quite less than that of stannous chloride. explain. Interesting. Check. In both the cases, the cation is of tin, and in both the cases, the anion is same, in fact, chloride. In stannous chloride, the charge of tin is 2 plus, Sn2 plus, right? In stannic chloride, it is Sn4 plus. That means the charge is more, and of the same atom, that means since the more number of electrons actually are given off naturally, the size of Sn4 plus is smaller than that of Sn2 plus, right? And the charge is more, so the polarizing power of Sn4 plus is much greater than that of Sn2 plus. That's why a more and more polarization takes place in case of stannic chloride. Polarization of the chloride ions actually takes place in stannic chloride, and which gives this phenomenon. In stannic chloride, the association is so less that it actually is a kind of a viscous liquid, not even a solid. It's very hard, very difficult to get stannic chloride in solid state. Or if you consider keeping the cation constant, if you consider different anions, that means say sodium chloride, sodium bromide, sodium iodide. Here, the ionic character of sodium chloride is maximum, which is greater than sodium bromide, which in turn is greater than sodium iodide. Why? Because the size of the anion gradually increases, isn't it? Fluoride, chloride, bromide, iodide. Fluoride, chloride, bromide, iodide. So since though the charge remains same, and we are dealing with the elements of same group, but since the size increases, its polarizability increases. So in sodium iodine ion is much more polarized than chloride ion in sodium chloride. That's why the covalent character is much greater in sodium iodide. Actually, it gives different. It can explain different other properties. You can actually explain different properties of so-called ionic compounds with these Fajan tools. It's very interesting. Like say melting and boiling points, solubility, electrical conductivity, etc. Or as you know, all depends upon the percent ionic character. The more the ionic character, more will it be soluble in water. More the ionic character, more will be its melting point. More the ionic character, more will be its electrical conductivity, and so on and so forth. Okay. And let me conclude today here, and we'll come with other periodic properties like ionization potential, electron affinity, and electronegativity in our next meeting. Thank you. Stay safe, okay, and be confident. Right. Thank you. Thank you very much.